So we have solved this question till this point that we found that this Q1 and Q2 are not in equilibrium because the magnetic field is making an angle of 90 degree. So this is 90 degree, again this is 90 degree. So these are not two in equilibrium because torque is not 0. For all others torque is 0. So at this point magnetic field is opposite to this. So that means this is positive MB because cos 180 degree. So this is unstable. Here it is in, if we go round and goes in the same direction, this is negative MB. This means this is stable equilibrium. This is not in equilibrium, this is not in equilibrium. If we go like this, so magnetic field is also in same direction. So this one is also a stable equilibrium, and this one was, if we go like this, so magnetic field is in this direction, this is in unstable equilibrium. So we have got that this and this are in unstable equilibrium and 3 and 6 are in stable equilibrium. So now we have to calculate what is the lowest potential energy of these configurations. What is the lowest potential configuration? So we have 4 configurations. This, let us mark is Q3, this one as Q6. So let me write Q4 first, Q5 and Q6. So this Q3, this is parallel, so this one is negative MB. So this is negative. Q4 anti-parallel, this is positive MB. Now this one is also anti-parallel, positive MB, and this last one is negative. So for minimum or lowest, we can have only Q3 and Q6. These two are not there as these are positive energy terms. So out of these two, which are stable equilibriums, only one can have the lower potential energy, other one will have higher potential energy. But now how can we decide which one has lower potential energy? So again let us see this diagram. You know this M is constant for this Q, MQ is constant. But what are two candidates? This Q6 and Q3. Q6 and Q3 are only two candidates for which this potential energy could be lower. So I should not mark it with this, I should mark with this arrow. So for only for these two, potential energy could be minimum. But if you see, this position is going in the mid. So this is equilateral. This is equilateral position and magnetic field here is BE. If you see here, so this is axial position. This position is axial. So magnetic field here would be axial magnetic field, that means B axial. And you know B axial is equal to 2B equilateral. Axial magnetic field is double of equilateral magnetic field. Now let us put these values. So if this Q3, so M remains same, this is E, this is minus 2 MBE, because this axial field is double of this equilateral field. So this one has equilateral, so minus MBE, this is axial, so M BA and BA is equal to 2BE. So this is minus 2 MBE. So definitely 2 is low, minus 2 is low than minus 1. If we put this line like this, so you know minus 2 is lowest. So which configuration has lowest energy? Q6. So Q6 has the lowest potential energy because it is parallel to the magnetic field, also it is on the axial position. It is not on axial position, this is on axial position as well as parallel to the magnetic field. So Q6 has the lowest potential energy. So let us check our answers. So what are the answers? Q1 and Q2 are not in equilibrium. This is the first answer. Now second answer, Q3 and Q6 are in stable equilibrium and Q5 and Q4 are in a stable equilibrium. Now third case, this Q6 has the lowest potential energy. So Q1 and Q2 are not in equilibrium, Q3 and Q6 are in a stable equilibrium, and Q5 and Q4 are in an unstable equilibrium. So this is the end of this question. Now we have to see the Gauss law. Now in chapter 1 we have studied Gauss law for electrostatics, so that we have already seen. In figure 5.3c we have seen that for a closed surface represented by 1, the number of lines leaving the surface is equal to number of lines entering in it. This is consistent with the fact that no net charge is enclosed by the surface. However, in the same figure, for the closed surface second, there is a net outward flux since it does not include a net positive charge. So what they are saying is figure 5.3c and surface 1 and surface 2. Let us go to figure 5.3. So here we are at figure 5.3c. So they are saying these two loops, this is the first loop, this thing is the second loop. Suppose if we see this first loop, number of field lines entering and number of field lines going out are equal. Why? Because there is no charge enclosed by this surface. Now if we see this second loop, this is our second loop. So here you can see that field lines are only going out. Why? Because in this case a positive charge is enclosed by this surface. So here the electric field lines are going out. Here the number of lines entering inside and number of electric field lines going outside are equal. Why? Because charge enclosed is 0. So for more detail you can see chapter number 1 where we have discussed this topic in much more detail. Now the situation is completely different for magnetic fields. Here they are saying that the situation is completely different for the magnetic fields, which are continuous and form closed loops. So magnetic field forms closed loops and there is no single point where it goes outward or inward. So there are closed loops. Examine the Gaussian surfaces represented by first and second of figure 5.3a, that means bar magnet, or 5.3b, that means the solenoid. Both cases visually demonstrate that the number of magnetic field lines leaving the surface is balanced by the number of field lines entering in it. The net magnetic flux is 0 for both surfaces. So if we see, we will take the example of a bar magnet and we will see both the surface 1 and 2 for bar magnet, and we will find that net magnetic flux is 0 for both the surfaces. This is true for any closed surface. So let us go again for this figure 5.3a. So here we are at figure 5.3a. So let us take these two areas. This is area 1, this closed loop 1. So number of field lines entering is equal to number of field lines leaving this surface area. Again if you see here, so number of field lines entering and number of field lines going out are equal. But in case of electric charges, here both are equal. So same line are entering, same lines are coming out. But at this positive charge, at this positive charge, we can see some lines are only going out from this side as well. So there is nothing which is coming inside. So the situation for magnetic field lines is completely different from the electric field lines. So hence there is no net inward, no net flux.